This video is for Chapter 2, Section 7, Inverse Functions. So if everybody would please get all of their stuff ready, we will get this one rolling. The book page that you need to be on is page 222. And here we go. So inverse functions. This means if two functions are inverses of each other, the domain of the first will be the range of the second, and the range of the first will be the domain of the second. So if you were to line up all of their x, y points and just swap them, if that is the case, those two functions would be inverses. For example, if we had an ordered pair for f of x, or a set of ordered pairs for f of x that are 1, 3, or 0, 3, 4, 5, 6, 2, if we found our inverse function of x, then we would find ordered pairs 3, 0, 5, 4, and 2, 6. See how they're just the reverse of each other? The domain of one became the range of the other. Okay, and that's exactly what inverse functions mean. We've just studied composition of functions. All right, if you were to take a function and its inverse and do their composition, you would end up getting the identity function. Now, if you remember back, the identity is, if you're thinking about your own identity, it's yourself. So if you're looking for the identity of x, it's x. So in other words, if we were to do the composition and plug f inverse into f of x, we would end up getting x back when we put x in. Oops. So let's take a look at checkpoint number 1 on page 222. It says find the inverse function of f of x is equal to 1/5 x, and then verify that both f inverse of x and f inverse of f of x would in fact be identities. All right, this is not as difficult as it sounds, so just hang in there with me. Now notice that f of x is x being multiplied by 1/5. So the inverse is the undo of that. So if the function f of x is 1/5 times x, the inverse function is going to be x divided by 1/5 instead. Okay, so let's break this down. That's going to be simplified by taking x times the reciprocal of 1/5, which will give us 5x. Okay, so that's our inverse function. So if we're going to do these compositions now, we need first f of f inverse of x. So if we were to take f of 5x, okay, plugging 5x in for the x's of our initial function, instead of having 1/5 times x, we're going to have, we would have 1/5 times 5x. Okay, so plugging 5x in for that x in our f of x function. And if we were to simplify that, we're going to have 5x over 5. And if you reduce, you do in fact get x. All right, so those two work. Now let's do it in reverse order. If we take f inverse of f of x, now that means we want to put the f of x function into our inverse. So the f of x function again was 1/5 x. If you put that into your inverse function, you're going to have 5 times 1/5 x, which again is going to simplify to make x. So there we've shown that both of them are, in fact, we've verified that they are inverse functions because we did end up getting the identity back. When trying to find if a function is an inverse of another, do the composition of the function and see if you get the identity. Okay, so if you're trying to figure out if one is an inverse of the other, do that composition thing that we just did on the previous page and check it. So if we were looking at checkpoint problem number 2 on page 223, it asks us to do this. It gives us the f of x function, x minus 4 over 7, and it asks which of the functions is the inverse of it. Well, the only thing you can do is check. So if we were to check the first one, g of x, that would mean we want to do the composition of f of g of x. So we do f of 7x plus 4, and that is going to look like 7x plus 4 plugged in minus 4 over 7 in that f of x original function. All right, so let's simplify. The top becomes 7x plus 0, or 7x, over 7. We get x. So that's looking pretty good. So one would assume then that the h of x is not an inverse, but let's go ahead and check it anyway. So we want to take f of h of x, which would look like this. Put the 7 over x minus 4 in for x. And we have to do some simplifying here. The top part, we've got a fraction minus 4, so we do need a common denominator. Simplifying the top, 7 minus 4x plus 16 over x minus 4, and that's still all over 7. And I'm going to write it 7 over 1 now, because now I'm looking at a fraction divided by a fraction. In order to do that, we're going to multiply by the reciprocal of that bottom fraction. So we end up with, I suppose technically that top would have been, what, 23 minus 4x? So we're going to get 23 minus 4x times 1, which is 23 minus 4x, all over 7x minus 28. Well, I think it's pretty clear in looking at those two, that numerator and that denominator, that they are not going to reduce away and leave us with x. So this one was not the inverse of our f of x. If you're looking at a graph of an inverse function, okay, what you need to be able to find to prove or show that something is an inverse is all of your ABs for one graph have to be in BA order on the other graph. So for example, if your one function had the point 1, 3, okay, the inverse function would have to have the point 3, 1. Okay, so it goes back to that first slide where we were talking about how the domain of one becomes the range of the other concept. So when you're looking at pictures of two graphs, okay, you can just do that kind of comparison. Take a look at the ordered pairs of one, compare them to the ordered pairs of the other. These inverse functions are reflections of each other. Okay, we've talked about reflections before. We know what they look like. So like I was kind of saying a couple seconds ago here, in order to tell whether or not you have inverse functions, find a few ordered pairs that satisfy the first function. Then, of those, take the range, take the y values, and plug them into the second function for x. When you solve, you should end up, if they're in fact inverses, you should end up getting the x values of the first function. Okay, so in other words, put all the y's you found for the first function in for the x of the second. And if your results that you get are the x values for the first, you know that those two functions were inverses. I know it's very wordy, but it comes down to that concept that the x values of the one become the y values of the other. The y values of the first become the x values of the other. So let's take a look at this one. So sketch the graphs of the inverse functions on the same grid, and then show that the graphs are reflections of each other on the line y equals x. Well, the line y equals x is just the diagonal with a positive slope going through the origin. So if we're going to graph that first function, we have f of x equals 4x minus 1. That's just going to start at -1 and have a slope of 4. So there's the function graph of f of x. We're going to do the same thing now for f inverse function. So if we're looking at f inverse, they give us 1/4 times x plus 1. Well, let's go ahead and do some simplifying here. That's 1/4 x plus 1/4, right? So if we're going to graph that one, the intercept is 1/4. And the slope is up 1/4. That little -1 back there. Okay, so when you're looking at this one, do those lines reflect over the y equals x graph? Which is that red one that I just drew. Okay, so yes, in fact, those things do both work out. Now, just to prove this a little bit, let's do some f or some xy points for each of these. Okay, so I'm going to make a little xy chart for my first function. And I'm just going to stick in the values 0, 1, and 2. Okay, so I'm talking about this function right here. If we put in 0, we're going to get -1 out, right? If you put in 1, you're going to get a 3 out. If you put a 2 in, you're going to get a 7 out. Would everybody agree? Okay, so now let's just test that with our second function. Now, if these two are in fact algebraically inverses, I should be able to take that range I just found and put it in as my domain in this one. If we put -1 in, we're going to get 0 times 1/4, which is 0. If we put a 3 in, we're going to get 3 plus 1, which is 4, times 1/4, which is 1. If we put a 7 in, we're going to get 8 times 4, which is 2. So now take a look at those sets of ordered pairs, and you can see that flip-flop of the xy's turning into yx's. One-to-one functions. If each dependent variable, which is the y variable, has exactly one value of the independent variable x, then a function is called one-to-one. One-to-one functions are the ones that are going to have an inverse function. Okay, so there's a quick test to tell whether or not there's going to be an inverse, whether or not you have a one-to-one, and it's called the horizontal line test. Now, if you remember how the vertical line test worked, the horizontal line test is the same exact kind of concept, except for it's horizontal, not vertical. So in other words, if a horizontal line passes through a graph only once, the graph will have an inverse. So let's take a look at this. Checkpoint problems number 5 on page 225. Just use the graph of f to determine whether the function has an inverse function or not. Now, if you're looking at f of x equals 1/2 times 3 minus x, that one's going to end up being a linear equation, correct? You're going to have a slope, you're going to have an intercept, and it's going to be a straight line. Okay, so this one would be the same as 3/2 minus 1/2 x. Okay, so without having a real precise graph, it's going to start at 1.5, and it goes down 1/2. So here's just a quick sketch graph of that function. All right, so if we started drawing horizontal lines, would any of them pass that graph through more than one place? And the answer is no. So this one is a one-to-one. It will have an inverse. Okay, let's take a look at f of x is equal to absolute absolute value of x. Now we've been doing enough work with these that we know the parent function of absolute value is v-shaped. So let's perform our horizontal line test again. Do you see how it crosses the graph twice? This one has no inverse, not one-to-one. Now, we looked at finding inverse functions a little bit on an earlier slide, but here's an actual process that you can use on all of them. Step number one, first of all, see if it's even possible to come up with an inverse one. If it doesn't pass the horizontal line test, the rest of these steps would be pointless. So use the horizontal line test to see if there's going to be one. Step two, replace f of x with y. Okay, we've talked about the fact that they mean the same thing in the past, so that's not a hard step to understand. Now, step three is where the actual process comes to play. You're going to switch all y's, that should be y's, not y apostrophe x. Hang on, I'm going to change that. And you're going to change all of the x's to y's. Then solve for y. Okay, once you have, you're going to have y is equal to something, something, something with your x's over there. Then put inverse of f back in for y so it's in function notation. Okay, and again, we can always use that check with your domains and ranges to verify that in fact you have an inverse going on. So let's take a look at this one. Okay, this one's checkpoint problem number 6. There's one done out for you in your book right above it. But let's find the inverse function of this one. All right, so our first step said to try the horizontal line test on it, and I'm just going to cheat and tell you that it in fact would pass. Okay, so we can in fact find an inverse function for this particular problem. All right, so then step 2, replace f of x with y. Step 3, switch the y's to x and the x to y. So this becomes x over here, and we end up with 5 minus 3y over y plus 2 on this side. Now we need to solve for y. All right, so let's first of all get y plus 2 out of the bottom of the 1 and over to the other side. Okay, go ahead and distribute. Now, if we're solving for y, we want all of our y stuff on one side and all of our not y stuff on the other side. So bring the 3y over to join with the xy, and put the 2x on the other side with the 5. Okay? Now, you can't combine xy plus 3y, but we can pull the y out of there. So factor it out. Now, how would you get the x plus 3 away from the y? Divide both sides by it. So we end up with y is equal to 5 minus 2x over x plus 3. Now we can replace our y with our function notation, and we've got it. Okay. Let's do another one. Okay, this was checkpoint number 7 on page 227. We're going to find the inverse function of one that looks like this. Same set of steps. First, put y in. Switch them. And now we need to solve for y. Well, y right now is contained underneath that cubed root sign. So in order to get rid of the cubed root so we can get at our y, we're going to need to cube both sides. Last thing to get y alone is to subtract 10. And now we can substitute back in our function notation. So with a little practice, those become, I guess I wouldn't go so far as to tell you guys that you're going to think they're fun, but they become very doable. right, now, one of the assigned problems that I gave you is very similar to this one. So I'm pulling number 83 from the homework pages. I have assigned for you guys number 84. So I figured I'd go through one and it might help you out with your homework tonight. It says use the function f of x is equal to 1/8 x minus 3 and g of x is equal to x cubed to find the indicated value. Now notice we've got a composition going on here and we need two inverse functions. All right, so let's first of all find our inverses. Okay, so f of x is equal to 1/8 x minus 3 right now. Let's go through our steps in our process and come up with our f inverse. So I've just swapped my y's and my x's, and now I'm going to solve for y. So that inverse function looks like this. So now let's do the same thing for g of x. Swapping my x and my y's. And now if I'm going to solve for y, I need to do the cube root of both sides. So g inverse function is cube root of x. Okay, now let's do our composition. If we've got f inverse of g inverse. Okay, our f inverse function was 8 parenthesis x plus 3. So in that x position, we want to put in our g. So instead of having 8 parenthesis x plus 3, we're going to have 8 parenthesis cubed root of x plus 3. Now, there's our composition function. We are asked to find the value of that function for the value 1. So go ahead and plug that in. Well, the cubed root of 1 is 1. So I end up with 4 in my parentheses multiplied by 8. This whole thing ends up with a value of 32. So a lot of steps of the things that we've been taught during this section, but they all just actually for last section, for 2.6 as well with that composition. But, you know, all of the pieces just come together and build to find this kind of an answer. All right, so you had to find your inverses and then do a composition using those inverses. Then take the value that they give you, look for it, in this case it was a 1, and just plug it in and solve. All right, that's it, folks. Do lots of practice problems. Do a lot of the odds. The 5 that I want on a separate sheet of paper this time. Okay, off of page 228, I think? 228. I would like 10, 14, 38, 40, and 84 handed in tomorrow. So let's do those 5 tonight. A couple of them are real quick. Okay, so there's a couple of them where you're going to just do a yes or no answer using that horizontal line test. So it's not real overwhelming. There's 5 here, but not all that time consuming. So come in with the questions if you have them. Otherwise, I will see you in class.